Okay. Cool. All right, hey everyone! Finally, the last part. We're Megan, and we're the first team, the Blue Raspberry team, and I'm Joyce. This is Aaron. This is Kayla, and Christmas will be online. So our project's name is like the biogeochemical, like non-mover UUV, like stand for not amended but uncruded, and Raspberry Pi is usually for so that's how the blue raspberry comes from. And then from there, our goal is that, okay, we want to develop an algorithm to adjust this vehicle's navigation to maximize its sampling efficiency to the biological target. So thing is like our goal is like three categories. The first one, okay, we want to have a function. We want to have the optimal path function. That's we build up the algorithm and then including the environmental variables. The second category is more technical one, is that because we're in Python, but then the robot system is more in a high level, like simulation place. So we want to like make this two different kind of language communicate each other. And we want to make this also reproducible and open source. So that future, if other robots wanted to use the same thing, they could also run our thing. And the last one is more about how to grab data efficiently. And then that will be we have a scripted workflow that you could grab oceanography model data, avoiding fully download the whole thing. You can customize the regions and time range and depth. So save some time and to work on it locally. So next, I will move to Kyla to talk more about our data and methods.
Okay, so we have this UUV, and that's controlled with ROS2 and Gazebo. And we are integrating numerical models into our UUV. So we have two kinds. They're both numerical, but there's a high resolution model, NEMO, that we access through Copernicus that will spit out like currents and temperature and salinity wherever the robot is in pretty much real time. And then we use some lower resolution models as well for computing some of the biogeochemical variables. For our simulation, it's a large scale UUV, so we're like want to reconstruct biogeochemical things like for entire ocean basins. So for this one, we are kind of following along the Gulf Stream. We're doing a transect across the North Atlantic Ocean, and so it's moving to the east, west. I get them confused. You see the direction that it's moving. And then in the cross section, the lawnmower word comes from, this is the path that the drone takes, kind of like an up and down lawnmower shape. And so when it's taking these profiles and moving like across and then down, across, up, and up, across, down, there are points around the lawnmower path that it can choose to kind of diverge and go toward. And so we have a function that makes it choose what optimal point to go like sniff in the direction of. And that's what the little triangles are showing. So it can kind of wiggle back and forth in its trajectory too. And that way it won't just be straight down. If it was straight down, you might miss something kind of interesting. What is, okay. So the main like quantity that we're going to get from the UUV is profiles of oxygen utilization rates, and that's a quantity that marine biogeochemists and climate modelers, oceanography people, it's of interest to all of them, and it kind of measures the oxygen consumption in the water column, and oxygen gets consumed in the water column when particulate organic carbon is sinking down, and then microbes or other heterotrophs break it down during respiration or like just decomposition in general. So if we have this quantity, then the uses of it are we can detect phytoplankton and algae blooms. We can monitor microbe activity. And then you can also, using mass balance and stoichiometric relationships, reconstruct organic carbon export by the biological carbon pump, which there was a talk on that yesterday. but there's not a real-time organic carbon export observing system yet, because you can't really directly observe carbon fluxes that well. So this is like what we want to get from our device. Okay, so how it's computed is it's basically apparent oxygen utilization over the age of water, and AOU is the difference between oxygen concentrations at solubility versus what's observed. And so it's like with the same physical and chemical properties of water, you might expect oxygen to be a certain concentration, and then what you observe, it might be higher or lower because it's been utilized or not. So one of our functions takes in temperature and salinity from the high resolution ROMS model, and then it spits out saturation oxygen, and our UUV computes O2 observed. I mean, it observes it. In the simulation, we used a modeled oxygen, but in the real world, the instrument would collect it. And then we get age from, okay, side note, part of the optimal path where there's the little triangles or diamonds that we can choose to go to, the function that chooses which diamond to go to wants to steer up and down temperature and salinity gradients, just to maybe catch features of interest rather than just moving vertically up and down. But yeah, so then the last part of the OUR equation, age is coming from the low resolution, a steady state, so like a climatological average model, OCEM. So I computed like age for, this is the average age of water for every model grid box in the model grid. And you can see these are different depth bins. So at the surface, it's all blue because the age of water is like 0, because the age of water is how long it's been away from the atmosphere. And then the oldest water, around like 1,000 meters, is in the deep North Pacific, because that's how ocean circulation works. It's like the last stop on the train. So we use that to finally get the OUR. And then I don't need to do this, but how it's solved for is that OCEM is a tracer transport matrix, like it supplies one of those, and then you can pretend age is like a conservative tracer and like solve for it. You can do that with any conservative tracer, where you set like the change in time equal to sources minus sinks. And if you have the physical circulation, you can solve for it. Sorry, I don't need to go into that. The results from our simulation.
Okay. So what you're looking at here is the sim we ran, which is the UV is this little triangle here going up and down. We had a fun data visualization problem. Like historically, this software was used with drones, which when they do a lawnmower pattern is like going across like the XY plane that you can see on a map looking down. We can't see that when it's going down here, so added a way to be tracking its depth. If we had more time, it would be really nice to have like published some of the like pretend sensor streams up. But oh yeah, actually, let me back this up for a second, because what we're okay. So
It is like returning the quantities
There
that
we go.
we're interested in,
yeah,
and responding to our like optimal path.
right. So this blue line is the path that I dropped on the map and sent as a mission to the vehicle. All these red lines, I left it in that we had run this mission like repeatedly over and over, so you can see like before the decision-making criteria were added in from the functions that were just described. It would just say like you sent this mission, so it's gonna just go to the blue line and follow it directly across. And each time I restarted it, you see the path go back. Once we added in these functions, now it's making decisions to seek out these quantities of interest, and that's now it's adjusting the path. We definitely had to make some simulation changes to just make it work with the data. So this was news to me how low resolution the data would be dealing with was. Like normally we would probably be talking about like a maybe a kilometer stretch total that we'd be surveying with the UUV. Instead, this is, I think, something like, I don't know, at least 1,000 kilometers, because the drone is, the UV is flying at 1,000 meters per second in this video. Which is what we had to do to make it, like, to get real data at the resolution that the data we had was. So here it is, it goes and does this mission. I'll jump to the end, pause to here and see it take a turn here. And yeah, again, the things we would do if we had more time, it would be nice to see the data like getting plotted on the map. All right, pass back to you.
Like,
Oh, these are mine.
leave it here and welcome any questions.
On your track there, I was expecting the drone, like you gave it a straight path, but I was kind of expecting the drone would be doing weavy stuff.
Yeah, oh, like you mean,
Yeah, I guess it weaves a little bit, but I thought it would weave more.
yeah, it's also like pretty far zoomed out. I think it is making like small tweaks.
Okay.
Some of it's just the resolution, but it also is like, it won't necessarily do that. It really depends on the data you have. So right now here we have it making a decision about how much to adjust the waypoint you gave it based off of 3 criteria. It's gonna like try to minimize its total distance traveled. Something about oxygen. And try to find the most efficient path based on the ocean current. So
The real-time data is like 1/12 of a latitude longitude slice.
Yep. How would you envision getting the real-time data to your underwater?
it needs some kind of like predictive function, so that can be like pretty inaccurate even. It just needs to give it some kind of way of estimating. So I don't actually know like what that would be, but do you?
Christian was gonna cover that.
So,
Yeah, I guess we'd probably have to predict it a little bit into the future, but we'd have like data from the day before at least.
Yeah.
I was also, yeah, that's something that we are still figuring out.
I'll put it on as a GitHub issue.
We
can assign somebody else.
That was also actually my own question. Copernicus, they will provide the data during the current time. So they don't run forecasts that you can get later data for your simulations of the creation you are trying to do. So I'm trying to see how you guys are going to solve that kind of problem. Are you going to run the model in forecast mode so that you can have the prediction of next day for your mission, or are you going to grab the data and then maybe calculate in time?
Yeah, I think the time resolution, time evolution is definitely a thing that we have been thinking about. Previously the NEMO's simulations, they have like time evolutions on that, and then we could kind of mimic what we did in the real ocean. Like, we don't know what's the next day is happening, and then we need to have the path for the next day, right? But for the sake of time, for this way, we just say that, okay, it's a steady state. We're just trying to figure out whether the score function is right and whether the script is writing in a logical sense.
Okay, let's switch to the next team.
My name is Syed. Deprosa, Ismat, and Dwight, and Dr. Ray. We are going to present next the zooplankton migration prediction using deep learning. And so Ismat would explain what zooplankton are.
Why do we care? Zooplankton are like generating biological energy and macromolecules, and they are central to trophic transfer and biological carbon pump. Also, DVM recognizes biomass over 24 hours and alters predator-prey encounter rates. So here we are like our model next day migration prediction can guide sampling plans as well as optimize and improve data interpretation.
So why this next day prediction is scientifically useful? So by exactly knowing that when zooplankton, how deep they go and at what time their migration pattern is. So we can reduce this misalignment between the instrumental sampling windows and target layers. And also we can try to understand that how environmental parameter can affect the migration pattern of the zooplankton layers. So Dwight would tell us about our locations from where we got the data.
Yeah, so this is the Northeast Pacific up here. This is Vancouver Island, so not too far from where we are in Seattle. And then just on the southeastern tip of Vancouver Island is Saanich Inlet. And this is it's a fjord, and it's kind of like a bathtub shape. So it goes deep in the middle, and there's a sill at the top, so the deep water becomes very low in oxygen, even anoxic during part of the year. And we have an observing station at 100 meters depth, about 100 meters depth. And so that's where we were getting our data from.
So the vertical migration mechanism in environmental drivers, so such as the surface irradiance and day length, and the temperature can affect the migration pattern and at what time they plan to move up, and the phytoplankton biomass as food. So this spatial and season variability can affect their pattern. And if we can, so we were thinking that if we can use these environmental predictors and try to understand that if we can learn some meaningful pattern about their migration migration movement, so we can maybe predict that in future how deep they go, maybe in a seasonal pattern, and at what time they move in a day, and what time they come back. So this is just a broader framework. So our acquisition data starts from 2008 to 2010. We have 2 years of data, and we did some bench model training and evaluation, so we can really make sure that we are developing a complex model makes sense. So we develop a multi-layer perceptron, which is just a feed-forward neural network, and then we did some evaluation using regression metrics, and then selected the model. And Prosa would tell you in detail how we did the deep data pre-processing and evaluation.
So since you had data from like 2008 to 2010, our target data, as Dwight and Said have explained before, we have an echo sounder somewhere down there. It's 100 meters away. So we had information every after 1 meter. So that technically means we had too much data to deal with, as well as the target data set itself, the feature data set itself. We had like salinity, temperature, pressure, and all that. So in order to have like more information to train our model, we had to like tweak or feature engineer our data to some extent, where we introduced lags to our target data set, as well as the feature data set. We also introduced deltas of the lags as well. So yeah. So in total, we had about 200 columns from 79 columns to 200 columns of our feature data set, and from 88 columns of our target data set to 29 columns. So because when you have different depths, you don't really want to predict, like, let's say depth 100, depth 99, 98. Somehow these will be correlated. So it doesn't really make sense to kind of predict the zooplankton migration at every particular depth. And some of the Python packages we use are the normal pandas, NumPy, and since we ran an MLP or feed-forward model, we used TensorFlow for that, and that's how the model architecture looked like. And yes, a simple normal known, we did 80-20 split of our data set. And so this is just to show how our target data set looked like after we did the different grouping.
So what you're seeing here is the signal information bundled up together for all the different depths that we had, and as well as the signal in terms of time at different depths. And you can see we kind of have a dominant signal around between 20 and 40, which kind of aligns with where the thermocline, you'd obviously like kind of see the thermocline, and that's what we saw in our data set. And we also saw this pattern, which we're still not so sure why. People in the room can help us with that. But we kind of saw there's like a pattern going on all around. So we might need your input to kind of decipher that. And moving on further, these are the results that we have, and Saeed is going to take us through.
So initially, we only use the environmental features to predict the signal, and which is actually pretty hard to predict the deltas, just delta signals just using environmental features. But for some of the depths, it was around 0.6 R square, which is not bad considering that we only use environmental features. So then we decided to use the lag features of the signals, that what was a day before the value of the signal at that particular location. So when we added those features, most of our predictions become very good, and we achieve around 0.8 for some of the delta depths. Dr. Ray can
Okay, I wouldn't say we have pretty solid scientific results so far, but we do have some insights. We find we can improve the model scale with selected targets, because before we didn't do this lab, but we just find that if we lucky the targets, we will find better projections. And we find some of the drivers have higher predictability than others, so we change the drivers at the end, very end. And the layer means versus deltas, they are different. Because layer means which integrate depth signals yielded robust predictions, but fine scale deltas were way more error prone. And we do have lots of limitations. I think because of the system itself, it's a bit chaos. Rapid mixing events and site-specific biases and etc. can also like make these predictions even harder. But we do have some applications and the next steps. We can do this layer mean predictions. They are actionable for adaptive sampling, while deltas should be treated qualitatively. And we can also add more cyclic drivers like hours and season or external forcing, wind and tide and lunar phase, because that will all affect the system, affect how it behaves. And we can improve, all this can improve those functions, and missing data treatments are also promising improvements in the future. And actually, I have to say we work until very last minute, until Alex had to kick us out of the room. So there's definitely more to research in the future, and we will continue contributing to this project. And if any of you have any insights to this, or you want to be our collaborators, or you want to talk with us, please feel free to contact us, contact our team. Okay, and then we made a song to you.
But it's the sound sharing.
Sharing sound.
Billions in motion where the cold currents flow, and we go round and around till the sun touches down. Vibration of us water-bound, diving deep before dawn. Sundowning blasts will shimmer like stars, seeking to pass. Hairy mouths open large, pulling carbon down where it belongs. Then we go round and around till the the sun touches down. Greatest migration of us water bound, diving deep before dawn. Hey, I see the land. Hey, I see the land.
Any questions?
I just want to add on to this. So Sayed Usama did not sleep last night, and he was modeling all night. And while modeling, he got bored, and he decided to use an AI to create a song. And we all liked it, but the lyrics were kind of clunky. So this one wasn't as good as the one he made, but.
I was gonna ask, where did you find Jack Johnson?
So what do you know about why or how the zooplankton do this diurnal migration? Are they actively doing it, swimming downward? It's not like a water heats up and cools down.
No, it's active.
Active.
Yeah, they feed on the phytoplankton near, close to the surface. But then when daylight comes, there's visual predators like herring or whatever other small fish that will come and eat them. So they go down. But for their body length, it's a huge migration. Yeah.
But the phytoplankton are not migrating, so they just
No, they get pushed around by.
push around. Okay.
Yeah.
I guess I have like a technical question of like how you separate between organismal size, and zooplankton can range anywhere from say 100 micrometers to say like 1,200 or so, and then you also have all the fish larvae that are migrating along and creating a lot of activity, feeding on these zooplankton in that upper water column during that DMP as well.
Yeah,
So just a lot of action taking place.
that's kind of a limitation of this. We were using data from just one frequency, 200 kilohertz. The more recent data has 3 frequencies, and you can differentiate sizes. But we didn't have enough time in this hack week for 2 years of that. To use the old data.
That's a really good question because I asked that at the very beginning of this project.
Thank you.
Thank you.
If you want to stay plugged in, I'll just share my screen.
Okay.
I think that should work. Yes. I'll try,
All right, incredible. Thanks, Mike. We are the GarageBand people. Sending RipTide remix for OceanHackWeek 2025. All right, so the opportunity that we saw as we were discussing on Monday is that, as everyone in this room knows, there's a lot going on in the ocean all the time. But for people outside of this room, they probably don't connect with that fact ever, probably, if not very often. And so our goal was to kind of create an interface that would allow people to engage with the ocean in a creative and accessible way. And we have quite a few bioacousticians on this team. So the way that we wanted to do that was through sound.
So essentially the vision was that we would be accessing a bunch of these different data sets from all across the world. There's thousands and thousands of different acoustic recorders that are constantly recording and transmitting data in real time to different servers, to different data sources. So our idea was to access all of those. We did not do that this week, but the idea is to access all of those, to pull all of that sound into a local area where you can pull a specific time or geographic location that you're curious about and get a chunk of just a raw data stream of audio data from that place, and then use automatic detection and different clip classifiers through machine learning or different signal processing techniques in order to pull out signals of interest. That can be anthropogenic sound, that can be biological sound, that can be seismology. Oh, that can be different earthquakes and things like that, basically anything in the ocean that's going to make sound. And then finally, the fun part would be mixing that all together into your own song. I don't know if you guys have seen any of those clips of musicians that take like a snap and they turn it into an entire song just by upsampling and downsampling. But that's the idea, is that anything can become a song. So that's kind of the vision. And then back to those data sources, some of the ones that we wanted to use for this project in this week and to start off with were Ocean Networks Canada, so looking to Dwight, and then also Orca Sound is a Puget Sound, Orca Sound, yeah, is a Puget Sound local organization, and they have a bunch of different hydrophones in this area, and that's really easy to access and open source, so that's another great resource. Ocean Observatories Initiative, OI, I'm sure a lot of you have heard of that, but there's tons of data coming from that all the time, so being able to access that data. And then for the seismologists, we have IRIS NSS SAGE, which is an organization that collects and deposits different seismic signals. So flowing from there as well.
Yeah, so I'm the earthquake guy, and for us to make the sound more spicier, we added a little bit of earthquake. And what we did was to pull our data from the online repository known as IRIS. So I did a little bit of basic processing, which was to remove the instrument's response, like removing the effect of seismometer transfer function, also to convert from digital counts to actual measurement. And in this case, we're using velocity. I did a little bit of detrending to remove the linear drift of seismometer due to temperatures, power, and the rest of them. To also improve the signal to noise ratio, I did a little bit of filtering using a band pass, high pass, low pass to remove high frequency noise, low frequency noise, and all. So we incorporated all of this. We also did a little bit of picking different seismic arrival time, the P wave, the S wave, the SKK S wave. Here we go, the surface waves, and we incorporated all of this and converted them to audio files.
Oh, yeah. And then on the biological side, so similar to the humpback whale songs that everybody can hear, they're trying to go to sleep. There's lots of different types of marine mammal calls in the ocean. So we pulled a bunch of those together. In the future, we would love to have that auto classifier that pulls these signals from raw streams of data. However, for this week, we just used templates from those same sources, which are already pulled out and they're really easy to use, have great signal to noise ratio. So that's what we did for the biological sounds. Then we also had some anthropogenic sounds thrown in there and some other miscellaneous sounds.
So speaking of that automated classifying, it's a very active area of bioacoustics research, and it's actually somewhere where Casey and I do a decent amount of work. The goal ultimately being able to do automated detection at scale of hopefully every species in the world, but you know, stay tuned for that. So for this particular project, one of the initial visions was to be able to do kind of some basic detection classification, assuming that we were pulling from those live hydrophones. By about Wednesday, we decided not to do that for this week. But in the future, we would also like to integrate trained neural networks to detect and classify clips. Again, not so doable in 2 days. But I wanted to talk a little bit about the spectrum cross correlation because I spent a lot of time on it. Let's go to the next slide. So the way this works is that we look at a spectrogram that's represented ultimately on the back end as a matrix, right? So we have a template sound. So here, this is an example of a bowhead whale moan. It was not pulled from this target sequence of bowhead whale moans, something different. But basically, we compare the matrix of this spectrogram to the matrix behind the scenes of the target spectrogram and look for the areas where cross correlation is highest. So if we go to the next slide, basically we wind up with these correlation peaks. We identify the points where the peaks are highest relative to the surrounding data, and then that pretty decently well identifies where some of those calls are. So that was kind of the idea, to do kind of a crude, grab the best examples of the calls from that bigger data set. But for the demo that you're about to see, we mostly just used pre-sampled clips to kind of make it easier.
So as Maggie's talking about, that would be a great actual goal for the project, but it's like a hack week project in and of itself that would take multiple hack weeks. So the big part that we focused on was the audio mixing to get our really cool deliverable that we have in a few slides. But essentially, we were pulling those audio files as templates, doing your basic audio processing, like increasing the speed, increasing the pitch, increasing amplitude, or decreasing any of those, looping it, changing where the start time was, as your GarageBand over there on the right would do for you. So right now, as it stands, you could just download all of these template files and put them into GarageBand and do what we were trying to do. But that's kind of what we were trying to emulate, and we got pretty close. So.
For the interface, so you all know I'm a web developer, dashboard or whatever. I do not normally work in Marimo, but I really wanted to learn a new package this week, so that's what we went with on Alex's suggestion. I know there's one other group, so I'm excited to see what you guys ended up doing. Learning experience for sure. We struggled a lot with getting the code to actually work with the interface, but we did end up with, and you'll see this in a second, we did end up with some drop downs, some sliders, some buttons that'll update things. So if you're looking for a package to do some really relatively simple Python integration to make it kind of nice and user-friendly, could be a good starting point. But I think in the future, we're going to move towards maybe something more like Django-based or a little bit more like tweakable, I think. But we've got a demo where we can show you what it looks like.
All right, I am really proud of all 5 members of the team. They worked really hard, and I'm stoked to show for the first time our RipTide Remix website. Oh. Also, we have a little bit of a delay from my screen to here, so you guys are going to have to bear with me. So this is our website. It's hosted right now on my computer, so it's a bit slow, and we have a little bit of a delay, but I'm really proud of it. So when you come to our page, a lot of our intention was for public education. So if you come to our page, I'll first click through the things that are not as exciting. We made a template learn more page. This will be updated in the future with more information, but we just wanted to show kind of the intent of you can come and learn about all these sounds in the library and all these classifications and read something that a researcher might write about each species that we care about protecting in our sound. And then we also made just a fun little about the team where kids can come and hear our researchers' favorite sounds of interest. Mine is a baby crocodile call, and Daria really likes the osprey, but I thought that would be fun for kids to come and see kind of a connection to the researchers working on the project. The last thing before the mixer is our gather more data page. I'll let this load for a second. So this is really cool and really interesting, and I actually learned a lot about earthquakes working through this page. So if a person wanted to come and they wanted to learn about a certain earthquake, say Alaska in 2021, they could choose any network and any station they like and choose a channel. This is going to take a second to load. Hopefully not too many seconds.
And ideally in the future, this is kind of one of the areas that we were talking about would be connected to that IRIS site. So as you were working through here, you would be automatically pulling from the IRIS database or another earthquake seismic database. So.
And it's taking quite a long time to load on this, but here you can see just some example stations that, or example plots that seismologists would use. So you can see this earthquake where it happened in red and the station in yellow. You can see the colors that is plotting are not super well, but you can actually see the P wave, S wave, and then the surface wave, and then the spectrogram there on the left of what the signal would look like. And then in future iterations, we'd have an add to library, so you could add this particular earthquake to your library. And now getting on to the most exciting thing. Here's our interface. So you can choose a clip that you like. So we'll go cetaceans. I like odontocetes, so we'll go odontocetes. And we'll choose an orca sound. Okay, you guys are following along. My computer is quite old, so the processing on the server is quite slow. But here's our song, and then the spectrogram will come eventually. And we can change the speed and it'll update the speed in the picture, and then we can play the song. I won't do that just for the sake of time, but you can play the song, quick update preview, and then we can add the clip to our mix. And then down here, we can press mix, and it will plot our mix, and we can listen to our new song. It's only one clip, so this song won't be quite interesting, so I won't play it, but
What? We promise it worked.
oh, it does work, yeah. I was gonna play a canned song. So that was just our earthquake, but we did make a song earlier that has bass beat. Oh shoot, I lost our slideshow somehow. Nope. Okay, hold on, sorry, there we are. We did make a canned song earlier that I'd rather show by clicking through right now and showing you all the songs you could possibly make. So this was our song from earlier, and I will, as a wrap up to our presentation, let you listen to it. So our song has a Japan 2011 earthquake drum beat. And our notes are humpback and Inca whales, and then we also have a sperm whale kind of like little click in there. And this is a very slowed down humpback whale call. Yeah, for the sake of time, I didn't want to try to remake all of that live, but I wanted to show you my favorite sound that we've made, and then we can wrap up.
Perfect. This will be very quick. We have a long wish list of things that we want to add to this. In the future, we did apply to the conference with Dwight, so we'll see if that comes through. But mostly we want to expand that network of data sources like we've been mentioning, and obviously improve the detection and classification, see if we can actually maybe even meaningfully add to some efforts going on there.
And then finally, also a huge part of this and a dashboard like this would be education. So you saw a little bit of the education side, but acoustics is kind of a black box for people who aren't able to get into it. So we also want to make this as an opportunity for people to learn about the sounds that they're listening to and mixing, and sort of learn a basic understanding of what audio is and how to work with it and how it's important in the oceans. So yeah.
And also how loud ships are.
Oh yeah.
It could really mess this up. Yeah.
Great. Questions?
More of a comment, but Dolly Parton used her nails in like 9 to 5 as music. So like this would be super cool to market towards artists, like incorporate whale songs. But the caveat is they have to donate to the North Carolina.
Yeah.
That's good.
Yeah, also a comment, like if this was at an aquarium, I would not see any of the other animals making music. I think this would be a hit.
Honestly, one of the biggest things I learned is how hard it is to be a DJ, so.
All right, hello, everybody. This is the team. I don't know who's a better representative. So Marcus.
Stevie.
All right, cool. And so our group name is Project Argo, and today our title of our talk is using Argo floats to assess the influence of hurricanes on physical and biogeochemical ocean properties. So our objective for the OceanHackWeek and this project was to create to use Python on our pipelines to create an exact match with biogeochemical Argo floats and also hurricane data to track any regions in the world. And then also to compare the plots of the biogeochemical properties before, during, and after the hurricane.
Cool. Well, I'll give a little background on Argo, because if you haven't heard about it, it's a super amazing global program. Basically, it's a real-time global ocean observing system with over 4,000 autonomous floats just out there in the ocean. Each dot here represents a float that I believe is currently active or was recently active. And they measure a lot of different things. All of them measure the core variables of temperature, salinity, and pressure. And I'll talk more about the biogeochemical Argo floats in a second. But They go from the surface to 2,000 meters depth every 10 days. There's also some deep floats that go all the way down to 5,000 or 6,000 meters, so that's pretty cool. Argo has been around for many decades now and is giving us a really amazing global view of the ocean interior. And more specifically, the BGC array of Argo floats has been growing a lot in recent decades. These are basically just souped up Argo floats with a bunch of additional sensors like chlorophyll, dissolved oxygen, nitrate, pH, particles, etc. And here's a nice plot of what the current profile history looks like over the course of BGC Argo. So there's definitely still some gaps, but this, is a really amazing and growing program. And also a lot of the floats are built at UW and at NOAA PMEL just down the road. So that was another reason we wanted to work a little more with some of these data. Yes. So for a quick description of an Argo float cycle, as I said earlier, they go every 10 days. So floats will get deployed on research cruises of opportunity, and they'll descend to their parking depth of 1,000 meters where they drift for 10 days. And then they will go down to either 2,000 or 6,000 meters and collect a profile on the way up. And then they transmit those data to satellite and they repeat the cycle. And so the data that comes out of Argo floats are, after you quality control them, these very nice depth profiles. Here's an example of like a temperature and salinity profile. And yeah, I think that's all I have to say about how the floats work. Now on to our workflow.
So we developed this workflow to collect the hurricane data from the IV tracks data, and then we wanted to combine that with the Argo float data so that we could track while the hurricane was going. So first we extract the hurricane information from the IV tracks. So the IV tracks data have each locations of the hurricanes with the timeline, and we used that information and made like a grid box, like a boundary around the hurricane at the point, and then searched into the Argo PY package. It's a Python package to access Argo float data. So we use that location boundary to search if any Argo floats were there during the hurricane. Yeah, so we co-locate matching float profiles within a defined range. We downloaded them and quality control them, and then analyzed the plot with before the hurricane, during the hurricane, and after the hurricane Argo float profiles. So these are the packages we've used. The thing is that we used both Python and R in one notebook file. So this first part is in Python and the after part was in R, but we were able to merge it into one single file. Yeah. Yeah. So these are the examples. So we've choose 2023, the strongest hurricane, and it showed that Idalia and Hillary was the strongest. So we plotted the track of the hurricane, which is in red over here, and each 3 dots, the color of 3 dots is before the hurricane was here, during the hurricane and after the hurricane, the Argo floats data. So actually, if you look at here closer, you can see that 3 of these before, during, and after are overlapped here, which means that we could figure out how this region was changed during the hurricane. So yeah, okay. Yeah, so this is the strong hurricane, and we can do the same thing and compare how different hurricanes affected the mixing of the ocean.
Yeah, so we, so far I've just chosen like one example and we'll show some profiles here in a second. But here's the more detailed location of the profile that was taken before, during, and after the hurricane. And it was somewhere in this region. Yes, and then I guess one thing to talk about as well, excuse me, these are both for the core floats that just do temperature and salinity, and the BGC Argo floats as well. So one thing that we're still working on is like how to specify like which one you want, or like just get data from the BGC floats that have chlorophyll sensors or oxygen sensors or all of the sensors. So we're wanting to add more specifics to our pipeline. So that's one future goal. But yeah, now we can look at an example depth profile. So the float that we worked with had oxygen as well as temperature and salinity. So colors are a little different. Blue is before, red is during, and purple is after. And so kind of just some preliminary things of note. The salinity like maximum gets shallower during the hurricane, as you can see in the red line versus the blue line. And we thought that this kind of made sense because of like enhanced mixing during the hurricane. Potentially that's like mixing up deeper water masses that may be saltier. We wanted to calculate mixed layer depth as well, but didn't quite get to that. And you can also see that after the hurricane, there's like enhanced oxygen in the surface ocean. So perhaps that's related to like increased production or like increased ventilation and from mixing. So these are kind of some of our ideas. We're excited to look at more profiles in the future.
So we also saw that the surface water becomes cooler after the hurricane. So that's
All right, and then we also wanted to look at stratification. While we couldn't really plot mixed layer depth, we wanted to see how does the stratification change before, during, and after. So before the hurricane, we see that most of the surface and subsurface is really stratified. But then during the hurricane, we see that part of that stratification was intensified and or is more stable in the surface layer. And then afterwards, you start to have a little bit different contour. In the deeper part of the ocean, you start to have a more or less stable. And this probably has to do with the kinetic energy that dissipates from the surface to the deep. So one of the things that would be great to kind of do in the future is calculate kinetic energy dissipation and the mixed layer depth, and also seeing how the penocline changes to have a better idea of how this energy that's dissipated from the atmosphere to the ocean affects mixed layer depth in surface and interior ocean. And so our future direction, so for one, improve float search code to specify for BGC variables, improve our code efficiency. We currently have 2 sets of code for R and Python. And we also realized there were some differences between both toolboxes, so it'd be great to have a more efficient toolbox for both. Update the quality control and plotting data for R and Python. Calculate the mixed layer depth. Realize that between GSW's package and the Python toolbox, the mixed layer depth isn't really there or functional, and so it'd be great to kind of have the idea of that, so we can have a better assessment of hurricane strength on ocean surfaces, and then plot the BGC variables and ask the question of, do hurricanes enhance nutrient delivery to the surface and trigger phytoplankton blooms, and also do hurricanes enhance oxygen levels at depth as well. So yeah, cool.
But do you have to calibrate the data between floats?
So a lot of the like QC guidelines are included in the data that you download. So there's different like QC flags as like people have gone through and like processed the data post float sending the data profile to satellite. A lot of folks in my lab actually work on that, which is pretty cool. So it's really nice though, because it has the flags included in the data, so you can know like, we want to extract the 1, 2, and 8, because those are probably the best data. We want to throw out the 3 and the 4 tags, because that's definitely bad, that kind of thing. So it makes it a lot easier. So shout out to people in my lab who do that. Yeah. Yeah.
But you talked about before, during, and after, and I'm wondering about the during. Are Argos smart enough to not come to the surface if there's giant waves and huge winds, and
No,
or they come up anyway?
They come up no matter what, unless there's ice. They have ice detection methods. So folks in like polar regions know not to come up with ice, but yeah, they can survive the storm. They're not at the surface for that long. Yeah, and one kind of cool thing about the workflow that we've developed is you can like tune the timeframes that you want to set. So you could set like, oh, like go grab the profile that happened 2 weeks before the hurricane, or count it as being during the hurricane if it's within a 2-day window of the storm track location, and you can set them to be different before and after. So that was another thing that we did this cool with.
Yeah, so for this project, I think we selected 2 days during the hurricane, 2 weeks before the hurricanes, and 2 weeks after the hurricanes.
It'd be cool if you could do like a section, like along the track line of the hurricane, if you found some of those points.
Yeah, like maybe in the region of Idalia, like in the Gulf of Mexico, where there's kind of a bunch in one small area. There were quite a few hurricanes where there wasn't a lot of data, but like, I bet you could do something like that over here. That would be cool.
And we developed the script in a robust way so that we can make this kind of selections. You can select a specific hurricane, or you can just give a timeline of, yeah, this is the time frame of before, during, and after the hurricanes.
How long does it take the Argo floats to go down and come back up?
Well, I guess how long does it take for an actual profile to be collected? I actually am not sure what the speed is that they ascend, but it's not like it doesn't take that long. Like I would guess like maybe like on an hour time scale to actually surface again, or 2 hours or something like that. So like, I guess for the purposes of this, it's okay to assume that it hasn't drifted a lot as you're collecting the profile, but you can never like exactly know. And the other thing that can be kind of challenging about Argo floats is that you don't have any GPS data of where they were at during those 10 days. You just know where they surfaced. So.
Does it transmit the data from when it's the drifting stage too?
No.
Okay.
Sometimes they can be set to collect data during the drifting stage, but again, you don't have like the exact geographic location. But
are they designed to mainly focus on the data coming from the profile, or and the drift is just to get them to someplace new? Or are they also looking at the data collected during the drift?
It kind of it depends on the float.
Oh.
Like there's some floats where they put UVPs, how it's called, or like gel cams to look at like sediment that's falling, and for that they will be collecting data all throughout the drift. So yeah, you can have like special floats that will have different applications, and you can program them different ways. And you program them to be on like a different sampling frequency, which is pretty cool. But for the most part, it's just the data that's collected from the profile.
Yeah.
Okay. Okay, one more question and last question.
So just out of curiosity, you guys had a great talk and everything. But did you guys find the eye at any point? Or was that a problem resolving at all?
We got the eye of the hurricane from the IV track, so we already know the center of the hurricanes.
Cool. Okay, good way to.
Yes. Well, so all of the points that we have are from the eye, right? Yeah.
Very cool. Thanks.
Right.
That is why when we are going to take the phase ocean color observation remote sensing data, we are going to get a realistic representation of the variable we are caring about. So like to use, incorporate into our model or something like that. So that is why phase is going to give us advantage to get our input variable for the model.
And I hope to convince you to care about some fish. So we have very robust long-term ecological data sets in the form of a bottom trawl survey on both the east and the west coast. For those that don't know what a bottom trawl survey is, essentially the Northwest and the Northeast Fisheries Science Center both have a boat and they drag a big net through the water, and then they sort and count and measure all of the fish that come up into the net, and they know bycatch and everything like that. So that leads to these massive data sets of ecological data. On the West Coast, we have data from the late spring to the mid-fall since 1998, so 27 years of data. And that is from Cape Flattery, Washington, all the way down to the US-Mexico border. So we have a wide scape on the West Coast. And then on the East Coast, we have 2 surveys in the spring and the fall, and those have been happening since 1963. So over 60 years of data, which is pretty cool. And that covers the essentially New England region all the way down to the Mid-Atlantic to about North Carolina and Cape Hatteras. In addition to the fish data, these trawls also have environmental data like temperature, salinity, conductivity profiles, and stuff like that. So we just talked about 2 really robust data sets, but Izzy, can you go to the next slide? They are even more powerful when they're combined together. So I said earlier, fish live in the ocean. So it's really important to put fish in the context of their environment.
And now that we've spoken about the data sets, we wanted to bring up the driving research questions here. The first one is there a correlation between phytoplankton abundance and fish presence? And how well does the PACE satellite actually perform? So in order to do that, we have to begin processing this data. So for the PACE data, I got it from NASA's OCI, Ocean Color Instruments, and I was able to create a code that queried whatever dates I wanted. So for this sake, for the West Coast, we wanted the West Coast dates from late spring to early fall. And they came as daily files, and we were able to stack them and put them into an X-array. And then the trawl data had these discrete points, and I was able to query the specific lat, lon, and time and attach chlorophyll data to it. And the cool thing is now the code is done and it's completely reproducible. You can put it in for your own lat and longs and time dates that you want. And as PACE data becomes more readily available, as time goes on, you'll be able to use it too. So now that we have this data, we put it into a species distribution model called SDMTMV, invented by Eric just down the hall. And this is a gamma model that also takes into account random spatial effects. So as we put it into the model, we got some really interesting results that Max is going to talk about.
Yeah, so in addition to like using that spatial mesh to help us improve estimates for out of sample areas, we're also able to use this relationship between PACE-derived chlorophyll data to help us predict the CPUE, the catch per unit effort of a series of fish that were collected on these trawls that we're interested in. And so just for fish that commonly occur on the western coast in these trawls that appeared in over at least 50 trawls, we ran through and performed models where our predictor is PACE-derived chlorophyll, where we have a random effect on space, and where we're predicting our response of CPUE. And so here we have this plot, and each of these lines is a different species. And then if these plots fall to the right of the line, then they're positive impact on CPUE, and if it falls to the left, then there's a negative impact on CPUE. And you can see that all of these dots falling on right on that 0 dash line shows that there's a pretty low effect just for this variable for most of these species models. But if you look at the bottom, there's a couple that seem to stick out. And there doesn't seem to be any tight correlation between mobile or more resident species either. And so at first pass, it doesn't seem like we're able to derive a huge amount of significance from pace data for predicting spatially where these fish are. But there are a few species that do seem to stick out. And if you move ahead, we actually did run the models across over 100 plus species. And so this top left plot, you see catch per unit effort. And so that's just from the raw trial data and kind of shows you the distribution of where we're seeing more of these species. In the middle plot, in a little more green color, that's our estimated CPUE based on our spatial random effect and our fixed effect of chlorophyll A. And so that kind of matches up with what we're seeing in plot A. And if you look at the far right corner, about 15% of the data was held out from the analysis, and then we used the model to predict on that. And then, so these just shows some of our residuals and shows spatially whether we're over predicting, under predicting, and if that's biased regionally. And so our bottom shows just a bar graph of CPUE on the y-axis, and on the x-axis, like these random sites that we pulled out. And you can see that the yellow bars indicate that we're slightly under predicting for most sites that had trials done. And so if you move forward, you can see that it changes a lot depending on the species that we're looking at. You can move ahead again. And so, yeah, the point of this was just to give kind of an overall, show the overall distributions of these species across the region. And this, we did a little bit more digging and tried to separate out based on like the trophic ecology, if we see stronger trends in which ones show relationships to chlorophyll A, but nothing sticks out quite yet. And if you move ahead, if we input a little bit more detailed diet, we still don't see any strong things sticking out. So I suppose the next step would be we were really close, but would like to replicate this on the East Coast, and then also incorporate a suite of other pace-derived variables, including some of the in situ trawl measurements as well. And that would give us a better picture of the relative contribution of pace with respect to more conventional data, environmental data being used for CPUE assessments. And then anyone else wants to finish it out, but yeah, if you have any questions, let us know. Thanks to John.
It's not one of the recent satellites, because I believe that there should be like kind of cloud correcting algorithm, especially for many of the recent satellites.
Yeah, so that was achieved. If you go back a couple slides and we look at the that green plot, like if you look at this, the middle plot at the top there, which is our estimated CPUE in the model, you can see that it's pretty spotty. So what we do is that we have a suite of trawls that were performed at different days. We used pace data from each of the days that each of the trawls were conducted on. That was used to train the model on the relationship between pace variables and the number of individuals that we were catching. And then you can predict on like use that model fitting to like predict on like a new day. And so this is just like a random arbitrary day of pace data that we're able to just like spatially predict on. And so, yeah, I think another thing would be you could look at how your predictions change if you're just predicting on like a single day or like an average week, month, or year. I think that would change. So there's like a temporal component to that we didn't focus on here. Yes.
Really great to see you got the whole pipeline working and you were able to, produce predictions. Even though, it turned out chlorophyll wasn't very predictive, but yeah, it's okay. I think we were talking about it that, one thing people are exploring with pace data is light attenuation. So how far light goes down into the ocean. And as Dwight said, you know, you have all these visual predators and they're really affected by light because that affects how well they can hunt. And there's been at least one recent study that was doing species distribution with light attenuation and finding for visual predators a relationship. I think that might be a reasonable thing to look at for some of those species.
Yeah, very cool. Yeah, PACE is definitely powerful. If you go to NASA's Earth Access website, it has all of the suite of products available. And it's really robust. It has a bunch of everything from light attenuation to absorption spectra to like, even on the East Coast, they have a phytoplankton classification. It goes down to the species level.
I think the thing that we were most bummed about is that the larval data is not aligned with PACE yet. So I think we could draw some really cool connections between the larvae and the satellite imagery, just because in my head it makes a little more sense because larvae are more connected to phytoplankton. But larval data is just time lagged in processing. So if anybody needs a job processing larval data, I'm sure someone would be willing to hire you.
That's definitely an important note. That's why there was that one plot showing the difference between kind of like prey preferences. So and like whether you're looking at like mobile or resident groups, but we still didn't see a lot of a trend because once you get past that larval bottleneck, like populations are a lot more like stable. So I definitely think, yeah, if you got larval data, I think we would probably see some stronger trends.
It is an issue on GitHub. So
if you take it up with Cow Coffee though.
yeah, honestly, yeah, it would be an awesome project.
You can add labels. Maybe we'll make a label OceanHackWeek. So we'll do that, and you folks can add some issues for that. Thank you.
All right, hey everyone. We are the Dashboard with Chatbot team, rebranded as Splashbot now. I'm Finn. Vinal, Boris, Aiden, Troy, Ava. Yeah, thanks for being here. This is also us. That's pretty into our whiteboard, so those are our alter egos. Yeah.
So coming to motivation, like like there are many sources that we get this kind of data, but like most of the includers, but they don't know like which database is source for their model and like how to access this data, and also like an easy way to visualize and analyze this data. So we came up with this chatbot idea. Yeah, so this is our motivation for this project. Boris.
Yeah. So our mission or our goal is to remove the barrier between finding the right data sets and the climate scientists. So we want climate scientists to analyze the data easily without coding and without any problems with data access. And it does this really well. So the idea behind this is, in the background, large language model we connected with advisor tool, which can go to the metadata and show it to large language model explaining what is the data sets. Then it can also have access to some code examples. So large language model can use these examples to build their own calculation. And we want to wrap it up in some user-friendly interface. And Ava's going to talk about it.
So here is the user face in question. This is, I guess it's kind of blocked, but Splashbot. So we kind of wanted to make it as easy as possible for people to use. So the first part, the map, where users are able to, drag in and out. They're able to select a specific point, and then in the bottom part, it will kind of update as you do that to see where you're selected. Because we're using a chatbot, to put in your token, and then finally, you're able to ask questions about that selected map area.
So next we're going to go through a few of our results that we got from using our chatbot. So on the left here, you see just kind of the query we gave it. And yeah, just asked it to do some sort of plot in the Indian Ocean, and it went and it identified the best data set based on the metadata that we have, and made the plot. And I guess also talking about continuing what Boris was talking about with your metadata and the kind of data it can select from. How you could expand this is just adding more metadata for different data sets, or like adding maybe a data catalog that it knows how to access. So it gives you a wider range to look from. Right now, we just have a few data sets that it knows how to speak to, and this is one of them. And then another example of extracting a time series, we gave the LLM some example code on how to make different plots. So it kind of has a frame of reference that it goes and looks for to make these sorts of plots. If it doesn't find an example that it likes, it can think and make and write its own code to make a plot.
And here is one of the really successful plot we have made just by using natural language, sending to our backend LLM structure agent advisor tool and every function we made for this to achieve this goal. And then eventually the chatbot will give out the data description, what the figure looks like, and show us, okay, what is this area and this variable kind of like information I care about will look like in this area. So like scientists later doing research in this area, we know it shouldn't be too off by this really basic look if they're plotting for their result. And we also have a LLM tutorial that was in Jupyter Notebook on the GitHub. How can I get to it? That folder contains all the basic backend data and in the .py file and Jupyter Notebook for starter beginners to understand how this really works and manipulate to use their own choosing is here, own choosing LLM server and how to get things there. Here, the tutorial, and we had the whole README to set up the environment only running in this report, only writing in this folder. And the first user want to create their own chatbot or similar function just for easier for their research can start by using this from the scratch to define the JSON for data catalog for their own data set and bridge that with the LLM agent. Data preview, we had an example here successfully run in the Indian Ocean dataset. And instructions to build this local small tool for them and see the final result they want. Here automatically. And this especially works for the big data sets because we go through all the variables in the data set that has the best match to do this plotting. And that was like can be manipulated by only limited to the data set you care about. Like literally just use this folder to optimize on your own side of research. And we also have like a final working version we'll show in several later slides.
Yeah, we learned a lot. It was really cool. I think the spoiler alert saying it worked really well was meant to be sarcastic.
Oh.
I'm not sure if that landed. But it does feel like we're close, and I think like with a few tweaks in the future, it could be really cool. I don't know how realistic, like it's pretty computationally expensive, so I think hosting it and actually having it out there for people, there might need to be some just redesigning and some things to consider before like actually going for that. But it seems like something that people would be excited about. So I guess, yeah. give it a try.
So I guess we'll show you what it looks like. I'm not gonna actually run the thing just because it's like kind of a 1 in 5 chance it's gonna spit out the right plot, and it kind of doesn't takes varying amounts of time. Oh, you did?
No, the next one.
Oh, that's fine.
This is a shout out to the Slack channel for bad plots. So these are just some of the, yeah, the ones that didn't turn out so hot.
Okay. Get rid of this bar. Okay, here is the actual Splashbot interface. So you're able to, drag and drop. As you change it, it changes the boundaries, and you can select a point, and it will tell you what point you're selecting. And then again, not gonna actually run the plot. So let's say you wanted to plot chlorophyll or the map boundaries that I had before for whatever day. Right now it's kind of spinning out, it's very messy. This was the first failed attempt when you were trying this, so it gave us nothing, but you can kind of see, its thinking process as it calls the agent. And then we ran the same thing again. And here's where you can see it actually did spit out what we were looking for. So in the future, obviously, with some tweaks, hopefully we'll get this on the first try. But yeah.
And also, add on to this, that tutorial was also the scratch of our first version working scheme like that. So feel free to play with it around and ask a question on how that really works to get to this.
Thank you.
We try to do one live.
Yeah.
20% chance.
Let's do 5 times.
Let's pick a smaller map region. Just go like here.
Can you do data downloads too?
We remove this option in our final version.
Yeah. The problem is, it's not very privy to how big the data set is going to download. So you're like, give me global averages for the last 50 years. It's gonna download like a terabyte of data. So first we added some roadblocks for it, so it wouldn't do that.
Yeah.
And then we kind of just bypassed the whole download step so that it does everything in memory.
And so the ones that you showed before, the failed query and then the query that ran, was it literally just the same query?
Same exact.
Yeah.
Okay.
It didn't actually fail. It just, we're having trouble getting Marimo to
Yeah.
find where it's saving the plots to.
And actually, this file was in the back end. It was stored in the folder and generated, but didn't show in the reply to the output.
Yeah.
If you ran the same, like prompts again a third time, would it show this plot again?
It has no memory at the moment. That's like a future step for sure. So it has prior context to your conversation. But yeah, now it's just.
But in theory, yeah, it should download it again and produce the same plot. Maybe we default color maps, color bar, but the values should be the same.
Is there any element of the output, and maybe we're about to find out, that it shows what data set is actually pulling and like tells user how to find it?
Yeah, so under the hood, right now you're just seeing this spinning button, but under the hood it'd be spitting out like all of the things it's trying to do. And so the first tool, the advisor tool, what goes and figures out which data set to use based on the metadata available. So it would tell you like, I'm trying to read SSD from this data set in this boundary.
Is there any like for a user function, like if I, as someone who has no idea what's going on under the hood, when used it, like would it spit out that map and be like, or is there any option in the functionality of spitting out that map and being like, this is the data set that we actually pulled this from and here's where you can find it?
Yeah, we've instructed the LLM to summarize like what it did look, but you know, it's not perfect.
Yeah.
Yeah, do you guys just hard code the metadata for now, or do you have a feature where you can change, so if a new data set like PACE comes out, or it'd be hard to incorporate into the LLM?
We have a basic schema that we follow, and you just have to kind of build a connector between wherever that base metadata lives and massage it into the schema that we have.
And you can find this part in the LLM tutorial folder. We have this Jupyter notebook that generates this JSON data log for you. But that so far we have all the data holding on the cloud. So it was like pulling their data from this S3, I think it's S3 mostly request. Then start performing all the later LLM work for you. So that was like a starter idea for us to get it work.
Did you guys use LangChain?
Yeah.
Yeah.
I have like one suggestion is that have you guys heard about multi-LLM, like multimodal LLMs? It's if it's accepting other things than text messages like images, that's called multimodal. And I guess you can make like a logic to reiterate itself, but like look at the plot that got at the first time, and then like it could, as an input, it could make it better themselves, like reiterate it. Yeah, it's one suggestion.
That's actually a super cool suggestion, and I think in my research institute, someone who actually did it, so they were making advisor for tools like, so this label is wrong, change it to another font or something, stuff like this.
Showing the truth.
Oh,
wow.
Right.
So my question is if we can have like an already like open APIs token and then, have their repository of metadatas kind of pulled in, like can we use their token to get more? So now the metadata is just the Indian Ocean or like the ones that you guys hard coded. Is there a way we can use their API for more generalized way of pulling the information and then
I guess we kind of created the metadata for our couple examples. So not out of the box, but you could definitely, I mean, you could develop some scripts or pipelines to build your own metadata, and then you're just basically feeding it to the LLM to give it extra context.
And also originally, so far we had 3 data sets, the ERA5 and the MER SST and the Indian Ocean data set. The ERA5 and MER SST are really huge and they were hosted on AWS. So we kind of, originally we wanted to use Array Lake. They have a virtual data set management way. So for us to directly asking to access to these cloud hosting big data set and then pull that to create our local data catalog and feed to the LLM and perform all the functions they need. However, they didn't have that documentation for us to do this setup in this week, so we had to write it manually to have this current data set catalog. But if their function really working and it's not really expensive, that's totally doable to transfer this hard-coded data log to automatically running and searching manual scripts like that.
They're hoping to let you make public virtual data set array lake instances free at some point, or at least that was the last rumor I heard from show. So hopefully in the future, we'll it'll be able to say like, hey, this data is elsewhere, but here's all the metadata in Array Lake, and here's the easy ways to query it.
Yeah, and there's also a dataset tracker Jupyter Notebook in our repository that shows how you to create this and track these, access this data set, start play with preparing data for the URL.
I think something that could be really powerful with this is like, you pick a certain data source, let's say like ERDAP that Felipe was talking about on or Tuesday. And if you figured out how to kind of extract a site-wide metadata or of all of the data available in an ERDAP, and then made that available to an LLM like this, instead of doing a text search for like water temperature or something, and like relying on some keyword search to go do that for you, it would know about this whole ton of data, and then it can go look at the metadata and curate a list of possible data sets for you.
Yeah,
based
that
on
was
research.
our original stuff as well.
Yeah.
Thank you.
Last talk, we're almost there. So our project was a continuation of a project from GeoHackWeek 2024, and it's focused on developing algorithms for filling in this case is chlorophyll A, but in general, filling in any gridded like remote sensing data sets like we've been seeing in the talks, and using neural networks. And the idea here is to develop a tutorial to demonstrate how to do this so that groups such as the Fishy Paste group who are dealing with this, it would be easier for them to apply this type of algorithm and do like it's kind of like an interpolation step to fill in all those gaps in the data. Next slide. Right, so why do these gaps appear in the data? Well, certain sensors don't go through clouds. In particular, the ocean color sensors are measuring the color of the ocean, and they're getting this like hyperspectral or multispectral data. But anyhow, it's color of the ocean. If there are clouds there, you can't see the ocean. And the we're focusing on this using this data set that was developed actually 3 hack weeks ago, years ago, on the Indian Ocean. And it's really a good data set for tackling this problem, because you can see the white are clouds, and you can see that there's a lot of clouds. And the Indian Ocean in particular is affected by these really strong summer monsoons, and it just gets really cloudy. But in general, the ocean at any one time, it's like well over 50% is covered by clouds. This is like a pervasive problem. So the other thing is, so it's not just filling in the gaps, but the other solution is, or that we're trying to give, put in the hands of scientists, is to help them develop regional gap filling. And why is that important? Well, there are gap filled products out there. One, it might not be the variable you want, but a bigger thing is that the algorithm is for the whole globe, and they kind of like optimize for the whole globe, but it optimizes for the whole globe, but it might not be the best algorithm for your particular region. And if you're looking at something like chlorophyll, maybe next slide, you'll see the pictures of see if we can see some chlorophyll. Yeah, you can kind of. So like, maybe you can see here, this color scale is, it did not benefit from the lecture on great visualizations. But there's these like really specific patterns that form in the chlorophyll. This is Somalia. This is a very famous upwelling. and you get these like swirls and stuff. And then this is another big upwelling region off the southeast coast of India, and they get really different features. So the idea is to use these two-dimensional convolutional neural networks, which is really good for images, and they can learn those patterns, which you'll hear about. And the eventual goal, like I said, is a tutorial, but also that can then be used to do things like test whether different forms of the model would improve accuracy. I think that's the end of my slides. Next slide.
Okay, so the data set we use is publicly available, I think. You can access from this organization. And it's the Indian Ocean subset. And because it's still big to us, so we are subsetting us even smaller data to this purpose. And the variable we care about would be the target is our chlorophyll. I think I don't need to re-emphasize how important chlorophyll is for our like oceanography data. It's like biomass for ocean, and it's like important for global carbon cycle. And the data sets provide all different kind of like prediction. It's like ocean atmosphere. For this particular work, we only use SST, but our goal is like you can use all of the predictor to train the neural network and to do all the like prediction as you would like to do. That, yeah.
Yeah, so as we were mentioning, we have a very small subset of the satellite SAR images that you see. So the data set from Copernicus is satellite images, basically, and those are SAR files which are n-dimensional and n-dimensional terabytes of data. And we are chunking it and slicing it to the parts that is latitude 107 to longitude, I believe 205. So it's like a grid on from the. So what's CNN? CNN is convolutional neural network of deep learning neural network for specifically images, and it can give us spatiotemporal features. And the thing about neural network is we don't have to explicitly say, oh, this is the eyes, go search for the eyes. It can iterate and learn the features by itself from the low level features like the edges. So this is like a face that you can see, but in our grid, like spatial means like the grid of the satellite images. Temporal all means like the last day we had chlorophyll, now there is cloud pixels. The next day we have temporal features as well. And also seasonal cycles, maybe during summer there's more phytoplankton, spring blooms, and so we are adding all those variables. Yeah, this is CNN. It kind of learns the features, and there's feature maps. In convolutional, it's just a mathematical operation where it kind of learns features. The next slide. So UNet architecture is a specialized convolutional neural network. It's one of the many types of neural networks available. Why UNet is better for our case is because of this U structure. If anybody can see it, it's kind of, it has an encoder. This part is encoder part, that's the decoder part, and these green lines are skip connections. So let's say we have a latitude, longitude, and 10 variables of features. So this is an image. This is just showing you 3 RGB image, but in our case, it's n dimensions. It's the latitude times the longitude times the 10 different variable features. So that is downsampled to its smallest features, and then the features that has been extracted is again like max pooling layers. It's more like layers. The features in the downsampling encoder part is then like the decoder part upsamples the image with the features. So at the end, you get the very like whatever output you want with like with the features that you intend to like. The output, the predicted output gives you the input. The input is the ones that you have with the variables. The model kind of trains to give you, okay, I need chlorophyll, give me like a model that can predict chlorophyll. The next slide. We are training a tutorial, as Eli mentioned, the last year's tutorial. They have this neural network architecture. It's the UNet one, and these are the 10 features that I was talking about. These are the 10 channels, including our satellite grid image. That's going into the input layer. As you can see, those are the input layers, and then it's like dividing by 2, then it gets divided over here, and then the decoder layer gets, I think I got the image, but a decoder layer. And it has these max pooling. Max pooling kind of reserves the features. It's just like all the spatial temporal features, it gets pulled back to the real one. Okay, next slide. And then we trained our model. This Copernicus data set, it's from 1997. You can actually train it from those so many years, but we had a problem with batching it, and we can use Dask or batches to train more regressively, but we kind of chunked and sliced to only 2015 to 17, validated in 2018 data, and tested on 2020 to 2020 data. Okay, next slide. This was our testing strategy. So once the model is trained, we want to test it to see if it is accurate enough. The testing strategy was to we have the Copernicus data set. We applied synthetic clouds, fake clouds of pixels. And then we ran the prediction model, and we evaluated its accuracy. Is the synthetic, is it trying to predict the chlorophyll where, is it trying to predict the chlorophyll in the synthetic, the fake clouds, trying to predict with the real clouds. The results were, as you can see, this map. This was the observed clouds. This is the one which we gave. These are the flags that we applied, like the fake clouds, and this is the predicted from the UNet model. And this kind of gives you the difference between the log. The white says it's it kind of predicted very well. The red kind of marks that it did not predict well, I guess. And the blue is it kind of predicted okay-ish. This is the comparison between the Copernicus ground truth with the UNet, and you can see, okay, there's something called absolute difference and difference. Absolute difference is it has more, it shows it's a better way of accuracy prediction. It takes into consideration mean square error, so that.
Yeah, that one's the total difference, and this one's the percent difference, because it's on the log scale.
Yeah.
But you might have a big percent difference, but if they're really small values, it's actually only a really tiny value.
Yeah.
Yeah, but you can see here the UNet model, doesn't do so great along the coastlines.
Mm-hmm.
So, that's not really.
Yeah, that was because we can do the model that you saw is just very few layers. We wanted to try the convolutional 2D with LSTM with more regressive model layers. So what this model does is kind of crops the edges. That's what I think when you downsample it. it divides by 2, so the edges are being cropped off when it tries to learn. So it gives you give a dimension, and the unit kind of crops the edges.
I think we can go through this. We can probably keep going.
Yeah.
This is actually from the past tutorial that this was developed in the previous year. And we were trying to get, a lot of what we were learning was like how to develop a tutorial for machine learning, because we had a lot of trouble getting that tutorial to run. But you'll hear about that.
We had a ton of trouble getting the tutorial around.
Yeah, since our time is over, just for complaining about a little bit. I was trying to run this Dinkai model, which is a model that people developed for doing what we try to do, but the problem with it is that it is already outdated, and they moved it to Julia, and I was trying to use their Python package, which is not so cool anymore because it used Python 3.8, and all the other packages are also outdated. But these guys use this Dinkai and also this other one, the EOF, to get filling phytoplankton, which was like a really similar approach, which with the one we had, but they used the Julia package, so they went successfully while we were not.
Well, you found it ran into memory issues.
Yeah, I skipped that. But yeah, I run off memory, and also I found out that this CAE kind of models need more memory than CNNs because it expands the image again. So yeah, and these are lessons learned. Don't recommend outdated packages. Be aware of memory. Existing frameworks can inspire, but they have to be adapted to the context. Also, collaboration and clear documentation can improve workflow, because this is what the problem we faced with the other hackathon tutorial. We didn't have a lot of comments, and avoid to NumPy.
Yeah, tutorial. Yeah.
Yeah, I think that like for me, like these were all the things we tried, the UNet tutorial, which actually you'll see in the next final slide. We did get that tutorial to run in the end. It was a lot of work. So now there is a Jupyter book and it runs through everything. And there are notebooks to show you how to run it. So got that tutorial that was developed last year to run, but it was really hard. And even though the tutorial was supposed to be completely reproducible, and the Dinkai also, it's a beautiful repo and it has all this information. It's supposed to be reproducible, and we could not get it to run. Yeah.
Yeah, one of the issue was it was converting everything into NumPy, and you need a very large RAM and memory too. So there should be a way of like chunking these terabytes of memory. We are talking about very big data.
Yeah. Yeah, so like they ran it, the person who ran it developed it, they had a laptop and it had a whole lot of RAM. But we're running on things that don't have a lot of RAM. And so like they didn't chunk it. They just like loaded the whole memory, all the data into memory. But if you're trying to make something that's reproducible, you need to put that work in to chunk the data so that Dask will like deal with it in little chunks and you can run it on a smaller RAM machines.
Question?
Yeah.
I have two questions. The first one is, how do you create your mocked clients create the mask? Because
They are the clouds 10 days in the future.
Okay. And then my second question was, how did you treat land in your training data? Do you mask it out, or?
we flagged it out. The land data just, it's one, so the neural network knows all this. So
Yes. I don't know if you guys plan to continue this, but I think something that's really interesting I found and really helpful when I'm doing machine learning is to plot the attention mechanism. So you see actually what features in your original that it's predicting on when it makes your new one and what it's paying attention to. And I found that's really interesting and maybe might help near the coast if it's focusing somewhere around.
that's a really nice one. We could like map a correlation which features is actually happening.
Yeah.
Yeah.
Oh, okay. Yeah.
Yes.
Is there interest, what do you think that adding drone surveys will help the model validation? Drones won't be impacted by clouds, especially on the coast at least.
I think that's a different question. That's like validating like even the chlorophyll that you see, that's like from this ocean color. So it does have information, but its ocean color is not actually like chlorophyll. And well, no, maybe it is the same question. Yeah, so the question is, right, yeah, how are any interpolation that you do or gap filling you do for clouds, how well is that doing?
Yeah, we can definitely validate with the clouds, but we are like in a large scale, we want these satellites that are daily, in a sense, collecting information, and scientists are using it to study like chlorophyll and cyclones and stuff like other variables, not only chlorophyll, to get us like if someone at the Bay Coast wants to like find something, it's like more useful. Can you like patch up these places and help me find out that there are clouds in next to it?
I have a question. So do you think about any temporal component because like chlorophyll moves to water quality changes methodological. So maybe when we mask random masking and maybe validation also I'm not sure how do you really make sure that predictions are not biased?
Your question is how can you validate when do you want temporal features to be, because it changes to seasons and days. We do have features for temporal, spatial and temporal, like we have the clouds, the day we are predicting, the next day, and also seasonal like time, like sign and cost time. So those are temporal variables that can help us predict the validation, but
how about model?
Yeah.
When there are extreme events, how model is performing when there are extreme events?
Yeah, you can go back to that slide that I said, just skip over that. That kind of gets, that shows kind of an example of trying to explore that, and that is showing, just think of the y-axis as how well it's doing, and the x-axis is month, and then the blue there is like how many clouds there are. So it's a different question, but it's kind of in the same vein of just asking, is the model performing poorly when there are a whole lot of clouds, which you might expect that it would. And so you can see that it is performing poorer when the cloud percentage is higher. And so this is when that summer monsoon is happening and it's really cloudy. And you can see the inaccuracy is increasing, but it's not like, I mean, I guess it is going up quite a bit from 0.1 to 0.25, but it's still, I'm waffling here. They'd have to use some other methods, but that's how like we had tried to, in like last year, how they had tried to like see if the accuracy is changing over time.
Something that I find very interesting. My research also is sometimes the lag from metrology, you don't really see the effect right away, and it may take some time for water quality of chlorophyll to really change. So maybe you can add there the model, sent to our something model can reduce variance from, something has happened, 24 hours for your 8 hours, so the biochemistry of water have changed. It may, because sometimes, when we, align the data, so we usually, harmonize based on the same day, same time, in near real time. But, something that I just find that, it takes some time, for the biochemistry to change the water.
Yeah, I think that would like come in like these explanatory variables. We just tried SST at the same time. But yeah, absolutely trying lag variables. I think there's a lot of other things that could be tried, once the batching is solved. Right now, only SST is in because it just blows up the RAM.
Yes, guys, this model is, as you said, it's a very 2D, there are various other better models, not like vision transform. Like there is, you can venture out more. This is a very, we were trying to run the tutorial that was last year's, basically it was, and also trying to batch it. That's the main, like challenges.
Yeah, I would say like the overarching goal is like you can plug in whatever variable you want to train the model and to output your stuff. Like it's just like demo. You can even not predict like chlorophyll, it's totally fine. Just like whatever input output you want to plug in.
Yes.
How did you match the land data? Did you use like pre-existing shoreline data?
The Copernicus comes with the mass.
Yeah, the data comes with the mass. Yeah, this data has land as mass, there's fake clouds, there is,
No, not
there's
the
Not the fake
real
clouds.
the
Because
real
like
clouds and the, yeah, and how that is like one day before, those data set. Yeah, I can show you that. Oh, I'm sorry,
Like,
the
yeah,
features
this
have,
is
we
all-
kind of feature map these variables, yeah, but the data set does come with
If you go back
around
to
22 variables.
There, back.
Yeah. Yeah, if you go through this website, you can see what the variables are. There's a lot of variables that this data set has.
Oh, also, Alex helped me to put our SciMe product onto Arrow Lake. But if anybody had access, you can check out there.
Is it like computationally feasible to rerun like the predictions a bunch of times to get like for each cell size, like a confidence interval? So that you could use that data and then just like kind of buffer, like kind of buffer, like if you're incorporating that into like other models, like you'll be able to kind of buffer your estimates a little bit. Like how many times can you rerun a prediction without it like?
You can rerun your predictions to your like, I do not understand the pixel images or.
Well, like DeanCare does that. DeanCare is designed to give you uncertainty. I didn't fully understand how they did it, but I think in the input, they use the uncertainty. They have like an uncertainty of the original data, and then they propagate that with the, like this Gaussian thing or another. But UNet, the one that we're using, it just gives point estimates. So like it wouldn't be real uncertain, like it might be to the extent like the fitting is a little random. Yes, that'd be variable, but for uncertainty, I think you really want to input the, yeah, this sort of quality and then,
More segmentation and more.
yeah.
It should be, once the model is generalized trained, you can train it in your own.
But they have a package, but it's in Julia, which is why we didn't run it. But other people, you know, Runa showed an example of how somebody successfully used it for a different application, so.
Right.
Yeah.
Thank you.
All right. Thank you.